Hello! We're going to be looking at Chapter 14 in these next few videos, which is all about acids and bases. So here are the various objectives that we'll be meeting by the time we're done going through Chapter 14, talking about what acids and bases are, how do you calculate pH and pOH, and even what that means. Moving into Ka, we'll be talking about acid-base properties with salts and some various trends that we see with strengths of acids. So first let's do a quick review of some of the different properties of acids and bases. So just, kind of some definitions, but more just sort of properties and characteristics of acids and bases. So first of all acids have a sour taste. And so think about anything you've ever tasted that is sour. It probably has some acid in it. Lemon juice, orange juice, Sour Patch Kids, sour Skittles, probably has something like citric acid or something like that in there. Bases, on the other hand, have a bitter taste. If you've ever gotten soap in your mouth, then you know exactly what that tastes like. Acids, they will turn a piece of litmus paper red. This is one of their little characteristics, so it turns a piece of litmus paper red. Bases will turn litmus blue. So there's lots of different indicators and things that we can do to test whether a substance is an acid or a base. One of them, you may be familiar with pH paper, but another one is called litmus paper. So one of the characteristics that they'd like you to know is what happens if you put a piece of litmus paper in there. And we'll kind of explore that a little bit more in lab and so forth. Acids, they have a tendency to corrode metal. So they can eat through metal. Bases, they have a slippery feel to them. And again, think of soap. That kind of helps you realize what's going on there. Acids have a low pH, so numbers 1, 2, 3, 4, that's how you know if it's an acid. Bases, on the other hand, will have a high numbered pH, so their pH will be greater than 7. 7, of course, being neutral. Now, both of these substances, because we will be talking about solutions, so solutions are aqueous, and these will be strong electrolytes and weak electrolytes, so both acids and bases conduct electricity. But of course, you remember from previous units, if it's strong, it will conduct electricity really well, and if it's weak, it's going to slightly conduct electricity. Another thing to review are what are some of the possible reactions you can get with acids. So just kind of go through these. This is a good time to sort of refresh your knowledge of predicting products and that sort of thing. One of the other characteristics of acids is that they will react with metals to produce hydrogen gases. Acids will react with oxides, that's one of these things, and hydroxides, that's one of these things, to also produce water and salt, neutralization type reactions. Acids will react with carbonates, there's your carbonate, to produce carbon dioxide, water, and salt. Now, one of the things you want to keep in mind, and we talked about this in another unit, or we'll come back to this time and time again, carbonic acid is a very weak acid. We'll define what that means. So for the purposes of AP, if you see carbonic acid, you want to make sure that you break it down into carbon dioxide and water. Alkalis are soluble bases. Remember what that means, soluble, but not all bases are alkalis. And then soluble alkali metals make strong bases and hydrogen gas. Okay, so definitions of acids and bases. There are lots of different models and different definitions that we're going to use. Now, your textbook goes into Lewis, acid and base, and you might get that in college, but for the AP exam, you don't need to worry about that. For your definitions of acids and bases, these are the two that you really need to know. First of all, that Arrhenius, he's the one that we usually think of with acids and bases, the idea that a formula starts with an H and ends with an OH. So something like hydrochloric acid or sodium hydroxide would be an example of an Arrhenius acid or Arrhenius base. The Bronsted-Lowry definition is the one that we're going to be using the most, and that refers to hydrogens more as protons, so a proton donor or a proton acceptor. So under that definition, a lot of your Arrhenius acids are also considered Bronsted-Lowry. But what the Bronsted-Lowry kind of does is expand our understanding of bases to include all kinds of other things, like ammonia. The other thing to keep in mind, and this is just kind of a vocabulary word, is you will run into these things known as acid anhydrides. These are solids that will form an acidic solution when dissolved. So a lot of organic acids are solid in form, but you really can't experiment with them or understand their behavior until you dissolve them in water. So just be aware of that particular definition. Alright, so we're in aqueous solutions, which means we have water. And since we have water, that means we have to realize some of the special characteristics with water. Water does this thing known as autoionization. What does that mean? Well, it ionizes all by itself. So if you have a container of water, and if you think, so this is liquid and this is liquid, it will actually ionize and form aqueous solutions of H3O plus and an OH minus. And it's because of water's special ionization that it is what we call amphoteric. Amphoteric means that it has both acidic and basic properties. It can act as an acid and as a base. And if you look at what it splits into, an OH, that's kind of like Arrhenius's model, and this H3O plus, well, that's actually the proton. That H3O plus is what we call a hydronium ion. The hydronium ion is what happens to the H plus when it's in an aqueous solution. So to kind of get a better picture of this hydronium ion, I'd encourage you to check out this YouTube video up here, or just kind of Google the Khan Academy type idea. It has a nice animation of what's going on. For AP purposes and for all other purposes, you can treat the H the same as you would treat the hydronium ion. Just know that in your books and in your practice problems and on the AP test, you'll see H plus written more as the hydronium ion. What happens is that the water sort of attaches itself to the H plus and forms this kind of unique little characteristic. I should say that water is not the only amphoteric substance. There are many others. For instance, the bicarbonate ion can be amphoteric. It can both donate a proton and accept a proton. So therefore, it is also an example of an amphoteric substance. That leads us to a discussion of the conjugate acid-base concept. So this stems from the Bronsted-Lowry definition. So remember that Bronsted-Lowry is about a proton donor and a proton acceptor. So what we have to be able to do is evaluate a system and decide whether something is an acid or a base, and then also discover what does the acid become and what does the base become, and that's what we call the conjugate. So an acid will form a conjugate base, and a base will form a conjugate acid. And the difference, I always kind of say, like, follow the bouncing proton, follow the H plus, what lost the hydrogen and what gained the hydrogen. So for this first example right here, HA, A is just sort of our generic formula for acids, and remember that usually acids have an H in front of them. So we'll use that as our sort of generic acid formula. So in this case, HA is acting as an acid, and then water in this case is going to act as our base. So what happens here? Well, because of the autoionization of water and the ionization of HA, because these are in aqueous solutions, so just kind of remember that your HA is going to split apart, so one thing is going to attach to something else. The acid forms what we call the conjugate base, which is this piece over here. The base forms what we call the conjugate acid. And the difference is a proton. This lost the proton and this gained the proton. Now let's come down here and take a look. Now all of this kind of looks like a bunch of nitrogen-based things, and if you know anything about bases, a lot of nitrogen-based things are basic, but one of these things has to be an acid. So what you kind of have to do is evaluate the product side and the reactant side and see what lost the proton and what gained the proton. And so in this particular case, ammonia is our base. How do I know that? Because if I come over here and I look at the NH4, notice that it gained a proton. So this becomes what we call the conjugate acid. I'm just abbreviating conjugate there. So the conjugate acid is formed from the conjugate base, which means that this substance is the acid. And then the acid, once it loses its proton, forms what we call the conjugate base. So all throughout this chapter we'll be identifying conjugate acid-base pairs, and it's really just kind of following where the protons go. Alright, so how do we know what's a strong acid, what's a weak acid, and what does that exactly mean if something is a strong acid or a weak acid? The only way you're going to know if it's a strong acid is you just have to memorize them. So they're going to be on this particular list. The three big ones, HCl, HNO3, and H2SO4, hydrochloric acid, nitric acid, sulfuric acid. If you don't know those, you're going to be toast. The other ones, HBr, HI, chloric acid, and perchloric acid, those are kind of icing on the cake. But if it's not one of those 7 strong acids, it's not strong. It's going to be weak. So by definition, what does it mean if it's a strong? So we just spent the past unit looking at equilibrium, and there's a reason why this chapter follows equilibrium, because like all those systems, these can also be found in a state of equilibrium. So when we're defining what a strong acid means, really we can think about it in terms of equilibrium. For a strong acid, the equilibrium lies far to the right. In other words, we can reasonably say that any sort of strong acid will dissociate just about 100%. Let me write that word in there. Dissociate. Realistically, it's a little less than that, but for all practical purposes, we can say that it dissociates 100%. So when you have a solution of a strong acid, you know, we talk about hydrochloric acid or something, you really don't have a solution of hydrochloric acid because the equilibrium lies so far to the right. What you really have is a solution of hydrogen ions and chlorine ions. So this kind of doesn't exist. It's a strong electrolyte, so strong acids completely dissociate. Weak acids, on the other hand, will dissociate pretty much less than 1%, so they hardly dissociate at all. Some will be a little bit more than that, and some will be a little bit less, but they slightly dissociate. So for instance, acetic acid, HC2H3O2, is found in a state of equilibrium. So let me write the equilibrium reaction there. So as it dissociates, as it splits up, and again this is all aqueous, so you have aqueous solutions of all this sort of stuff. What you're going to see is you've got a little bit of the acid and a little bit of the ions. Actually, sorry, back that up. You have more of the acid and a little bit of ions, so it doesn't dissociate as much. But we need to figure out some way to express that. So just like you learned with your equilibrium and your equilibrium expressions, we can do the same things for acids. So if you are talking about a weak acid, then you probably want to know something about its equilibrium acid dissociation constant. In other words, that measurement that tells you to which direction is favored. Is it the products or the reactants? And the good news is that a Ka, we call it A for acid, is set up exactly like your Kc, your Kp expressions, all that good stuff. Products over reactants. Bases kind of follow the same sort of idea. Your strong bases pretty much will go to completion in terms of dissociation. So your sodium hydroxide is going to dissociate completely into sodium and hydroxides. So kind of definition of a strong base. They will completely dissociate. They dissociate just at about 100%. Speaking in terms of equilibrium, the equilibrium lies far to the right. Weak bases, on the other hand, will behave just like weak acids. Now, how will you know if it is a strong base? Well, your strong bases are made out of the alkali metals. Remember, that's column 1. Lithium, sodium, potassium, rubidium, cesium. And these 3 alkaline earth metals. Now what you'll see is these are actually insoluble substances. They are on your solubility rules. Calcium hydroxide, for instance, is called lime and is not terribly soluble, but what does dissolve dissolves completely. So, and by definition, that's all a strong base means, is that it completely dissociates. So a weak base, you get a little bit of that hydroxide production, but not as much. And as you would expect, if you've got something that's weak, something that's going to be in equilibrium, that you can write a Kb. You can write an equilibrium constant. Now, to give you an example of this, I'm going to use ammonia as an example of a weak base. Now, here's where the Bronsted-Lowry definition kind of comes in, because it's kind of hard to see how the OH sort of pops off because there is no OH. But if you put ammonia in water, and again, this is all aqueous, you have to think about what that system is going to look like. So here's the Bronsted-Lowry definition of conjugate acids and conjugate bases. Ammonia is my base. Water in this case is acting as an acid, which means it's going to donate a proton. So it forms the ammonium ion, and what's left is the hydroxide ion. And now all of a sudden it makes sense why this is a basic solution, because now we've got an OH. So I can go ahead and write a Kb expression to show my basic equilibrium here. And I'm going to put the NH3 at the bottom. Now notice in my Ka and Kb I did not include water, because remember, water is a liquid and we never include water in equilibrium. We don't include solids, we don't include liquids, so water is never part of this. But if the water's not there, then we're not going to have a system to work with. Last thing in discussing our definitions of acids and bases, if you know there is a relationship between acids and bases. So for an acid, we have our Ka. For a base, we have our Kb. There's the Ka expressions. There's the Kb expressions. There is a relationship between them that has to do with Kw. If you know your Ka, and if you multiply it by Kb, it equals what we call Kw. Kw is the water dissociation constant. So I'm going to tie this back to the auto-ionization of water. So I'll put this kind of up here. Woo! So it kind of does that. As you saw in previous slides. Sorry, messing up here. The water is going to self-ionize into hydrogen ions and hydroxide ions. And this is liquid and this is aqueous. Now notice I didn't put it in the hydronium form. You can if you want to, but I'm just going to keep it simple with hydrogens and hydroxides so you can see it. I can write an equilibrium expression for the ionization of water, and we call that Kw. So Kw is water. And since it's products over reactants, it looks just like that. Now again, I don't put the water in there, the liquid water, because you don't include those in your equilibrium expressions. Now the value for Kw is constant, but at 25 degrees Celsius. So at standard temperature, your Kw is equal to 1.0 times 10 to the negative 14th, which then you can further extrapolate to understand that you know also then your concentration of hydrogen ions, that's a 7, and your concentration of hydroxide ions. But this only works at standard temperature. We'll do some practice to see what kind of happens, but if you remember from Le Chatelier's principle, your K expressions are temperature dependent. So if you increase or decrease the temperature, your equilibrium is going to shift to favor either the reactants or the products. In the case of water, this is just kind of a good thing to stick in your memory banks. Because K expressions are temperature dependent, if you increase the heat of your Kw, it will increase your Kw value. So think about why that is for a second. If your K is increasing, that means you have more products. So increasing the heat of your water is going to shift your equilibrium to favor the products. So if I'm going to increase the heat, it actually ends up shifting the reaction in this direction. So from there, hopefully you can kind of figure out, I wonder if this auto-ionization is exothermic or endothermic, given that the fact that this is going to move in the direction that the heat is used up. But we'll do some more practice with that. Next up, we'll talk about calculations. Oops, no, one more thing to talk about. Forgot about this last little slide. These are a couple handy dandy little charts to kind of look through, and they are in your book as well. The relationship between acid strength and relative conjugate base. So remember, the difference is going to be a proton. So if you know something is a strong acid, then you know something about the strength of its conjugate base, and this is going to become important as we move into our calculations. This table right here is found in your book, and it's worth a read and kind of going through and figuring out what are the different ways that we can talk about acids' strength. Now, this is just focusing on acids, but bases follow very similar patterns. So I'm kind of putting the two things together, but your book separates them out a little bit. Okay, and with that said, next up, we'll talk about calculations.